All right, so we have that h1 equals h2 plus v squared over 2. If we move h1 over to this side of the equation, then we can have h2 minus h1 as delta h plus v squared over 2 equals to 0. So let's do that. So we just said that this would be delta h plus v2 squared over 2 equals 0. Alright, so for an ideal gas, this enthalpy change is a function of temperature only. For an ideal gas, delta H is the integral from T1 to T2 of the gas-specific heat, function of temperature, dt. And what we'll like to do is use an average, a specific heat that's constant. So what we'll do, figure out Cp of T1, Cp of T2, maybe assume a linear interpolation between those two values, take the average, and use an average Cp to say that delta H is Cp. Oh yeah, actually, this should not be averaged already. That should just be Cp, and then we pull out and call this average Cp. And then the integral from T1 to T2 dt is just delta T. So it's bugging me now that that's not there. That's not average Cp. That's the Cp is a function of temperature. All right, anyhow, so we have delta H equals Cp delta T for the enthalpy change. So for the ideal gas, we could write then the average specific heat times T2 minus T1 plus V2 squared over 2 is equal to 0. We could divide or move V2 squared over here, divide by Cp, add T1, and figure out what the exit temperature is. And that would be kind of good to solve for. So let's say T2 equals, if we move T1 over here, it's T1. Then it's minus 1 over Cp, the average, times V2 squared over 2. And now we have an expression for the temperature of this gas as it's cooling down. So if you've ever had a fire extinguisher that's discharged very quickly, if you've had a CO2 canister, if you've had, if you play paintball, I can't think of other, if you've worked in a lab and you've accidentally discharged a bunch of nitrogen into your lab or something like that, you would notice that the canister gets very cold. In fact, if you have a CO2 canister and you just discharge it very rapidly, it'll get frosty, icy cold. And so we see that here with this equation. This is telling us that that temperature of the gas as it's exiting is the temperature of the gas in the container. So if it's just at room temperature, we have a high pressure and room temperature gas at the inside. And then so T2 is going to be relative to not only the velocity, but the velocity squared, right? We're going to subtract off 1 over Cp times this velocity squared. And next thing we're going to be very interested in is solving for V2. Having the velocity as a function of temperature isn't necessarily going to help us a ton. So we'll look at what we call polytropic processes next and figure out how to switch this over to a pressure. So if we have a known pressure inside of the canister, gauge pressure, we can rewrite this and figure out what the velocity will be based on a pressure change rather than the temperature change, because we don't necessarily know this. So that will be our next step.